Hello all, welcome back to Operating System course. So today we'll get started with the fourth chapter, that is memory management strategies. So first let's see the contents of the chapter. So first we'll talk about some basic or background of the memory. Then we'll talk about address binding, what is logical and what is physical address. We'll talk about swapping, paging, segmentation, etc. Okay. So first we'll talk about the background. So, as we all know, memory is the central to the operation of your system, right? So, your memory consists of a large array of words or the bytes, each with its own address. So, basically, the memory is divided into two things. That is, one is main memory, and other one is the secondary storage or secondary memory. So, main memory is like your RAM, and secondary storage or the secondary memory is your disk. Okay, so this main memory is relatively expensive and it has small capacity compared to your secondary storage or secondary memory. So, but the performance is high as well as the main memory is expensive. So your secondary storage or secondary memory, it is cheap but it is slow, but it can store large amount of data. So your CPU, it can directly access only the main memory and the registers built into the processor. So we have seen the basic structure of the processor in the computer organization first chapter, right? You had a processor, and that processor, it contains registers, then it contains MAR, MDR, these all things, right? So your CPU can directly access those registers and the main memory, not the secondary memory. Okay. So if you see the machine instructions, so they take only memory address as the arguments and not the disk address or the secondary storage address. So whenever a instruction is being executed, the data which that instruction needs, it should be either in the main memory or in the registers. Okay. If suppose the data is not in this direct access or direct memory, that is your registers or in the main memory, then they must be moved before the CPU can operate into it. Okay, so how does the process are kept in the memory? This is our question, right? So if suppose, let me draw here. If this is our main memory, then you have your operating system, then you have different processes, right? Process 1, process 2, something like this. So that means each process, it gets its own space or address in the main memory. So to make sure that each process, it accesses only its instruction and not other processes instruction, we need to determine the range of the legal address. That means we need to determine the range, the starting and the end range of the process where it can be kept, and it only accesses that part. Okay, so we need to provide some protection to each process, and that can be done using two register. That is, one is your base register and the second one is limit register. So to understand that, see a we'll see the basic hardware here. Okay, so this is your main memory. Fine. So first you have your operating system, then you have multiple processes that are residing in the main memory. So once these are resided in the memory, then the CPU would be allocated to these processes and it will start executing. Okay, so as we have just now seen, right, the processes, they are given a range of legal address. So in this diagram you can see here, just a minute. Okay, so let us consider this process. Okay, so base register, it contains the starting value or starting address of that particular process where it has been residing. So if you consider this process, the starting address of this process is this one, 340. That is the base register value or the base value. Okay, then you have the limit as 1,20,900. So this limit is nothing but from that 340, okay, from 340, if you add this limit 1,29,900, whatever the value you get, right? So that will be the range of this process. That so if you add these two, 340 plus 1,29,900, you'll get the value 420,940. Okay, now your process, this process, it has the legal address from this till this value. Okay, from 3,40,000 till 4,20,940 is the legal value of that particular process. That means this process, okay, it can access all the address from the value 3,40,000 till 4,20,939. Okay, so 4,20,939. So from this value till this value your process can access. If suppose your process try to access any other values or any other address apart from this, that means your operating system, it understands that your process is trying to access different process or the operating system process. So in that case a error occurs. Fine. So now let's see how this protection of the memory space actually works. Protection is nothing but one process, it has to access only its address. Okay, it cannot access any other process. Or suppose if you have this process here, right? This process can access only the address from this range to this range. It should not access any other process or any other addresses from the process that are kept in the main memory. That is why you have to provide the protection. Okay, so let's see the diagram now. So here whenever your CPU it generates the address, right? Here you can see CPU generates the address. That means it is trying to access some address, some location in the main memory, so that whatever instruction is kept in that particular location, it can be executed. Okay, so first what does the CPU do? It generates a address. Okay, then this particular address whatever the CPU has generated, it is checked or it is compared with the base register value. Okay, so if suppose whatever the CPU has generated some address, if it is greater than or if it is equal to the base address, okay, then it means that particular address it is belonging to a process. Otherwise it results into a trap or a addressing error. So let us consider one example. Say suppose your base register value is 1000. Basically we have a process, say P1, it is ranging from 1000 till 1050. It is the range. Okay, that means your limit value is 50, base value is 1000. So 1000 is the base and base plus limit is whatever you get here, 1050. If suppose your CPU it generates a address, say 1002. Okay, say suppose CPU has generated this address. Now first this address it would be checked with the base address. It is checked whether the CPU whatever it has generated it is greater than or equal to the base register value. What is the base register value? It is 1000. So this condition is true. That is 1002 is greater than 1000, right? Then what we do here? Whenever the condition is true, that is yes, we'll move further. Now you have to check another thing here. Your CPU address that is 1002, it is now checked with the base plus limit value. So it is checked whether the CPU address is less than the base plus limit value. In our case 1002 is less than 1050. That means even this condition is true. Okay, yes means true. So in that case only whatever the 1002 address is there, right, in the main memory, that particular location would be pointed and the instruction from that location 1002 location would be executed by your CPU. Fine. Let us take one more example. Say suppose 800 is what your CPU has generated. It is the address what CPU has generated. First this address is checked with the base register value. Is 800 greater than or equal to 1000? No, it is false, right? No here. That means your operating system will now understand that the process it is trying to access some other location which is not in the particular range. In that case, what will happen? A trap to the operating system monitor will occur. That means basically a addressing error would occur. If suppose, now let us take one more example. So say CPU has generated the address 1055. Okay. Now this 1055 is first checked with the base value. So 1055 is greater than your 1000, right? Again, this true condition here. Now next what we will check, whether this 1055 is greater than is less than 1050. In our case, what is the thing? It is 1055, right? So it is false. That means again a system error occurs, or the basically your trap occurs. So this is how you can provide protection to your process using your base and the limit registers. Fine. Now let us talk about address binding. So basically, as I said, CPU can directly access the main memory but not the secondary storage. Like I'll draw here CPU, it can access main memory directly, and main memory can directly access secondary memory. Okay. So when you store your data or the program, so it would be stored in the secondary storage, right? Basically your program would be stored in the disk, and that secondary storage we also call it as a job pool. Group of processes or n number of processes would be kept in the secondary storage or the disk, and that we call it as a job pool. Okay. Now whenever you want to execute that particular process or the program, first it has to be brought from the secondary memory into the main memory, and then CPU can be allocated to it. Okay. So your CPU, it cannot directly access this secondary memory. You can see these arrows, right? We don't have a arrow directly from CPU to secondary memory. That means CPU can access main memory directly, and main memory can directly access secondary memory. Now you have to understand here, your CPU, it generates address, right? In the last diagram we had seen, every time your CPU, it generates secondary storage address or secondary memory address, not the main memory address. Okay. So your CPU, it generates address. Basically that address would be present in your memory address register, MAR. Okay. So your CPU, it generates the address for the data or the program which is in the secondary memory, but it has direct access to main memory. So your operating system has to perform address translation. Why? Because whenever you store a program in the secondary memory, it cannot be directly executed. Why? Because your program has to be brought into the main memory, then CPU can be allocated to this particular program or process so that it can execute. Now problem is CPU, okay, it generates the address of the secondary memory, not the main memory. Okay. So your operating system, it has to do address translation. That is, whenever program is brought from secondary memory to the main memory, there would be address changes, right? That translation has to be done by the operating system. So your program has to go through many steps before finally getting executed. So why this address translation is needed? Because CPU knows in which location the program is stored in the secondary memory, but it does not know the location of the program in the main memory. So your operating system, it performs address translation or address binding. So binding addresses to the data or the instruction of a process, we call that as address binding. Okay. So this address binding can be done at three stages. That is, one is your compile stage or compile time, second one is load time, and the third one is run time. Okay. So before that, first let us check this diagram. Okay. So first you have the source program. So whenever the source program is compiled or assembled, so at that time you can do the address binding. Okay. If suppose, if at the compile time the address binding is not done, then the binding can be done at the load time. So loading, it means when the process is actually loaded into your main memory, that time you can do the address binding. If suppose even at the load time it is not done, then you have to do the address binding dynamically. That means at the run time, execution time, you have to do the binding. Okay. So now we'll see what is this compile time binding, load time binding, and run time binding. Fine. So first one is the compile time binding. So during execution, your program is compiled to the object code. So if the binding is done at this stage, we will call that as compile time address binding. The next one is load time. If suppose we do not know the exact location of the process during the compile time, then we delay the process, that is we delay the address binding till the load time. So loading time means when actually your process or the program, it is being actually loaded into the main memory. So if you do address binding at the loading time, it will be called as load time address binding. So the last one is execution time or the run time binding. So if suppose we do not know the address at the compile time or at the load time, then it can be done at the run time. That means dynamic binding. Okay. So this is about your address binding and the types of it. Fine. That's it for today. We'll conclude our session. Thank you.